All right, so we are looking
Oh,
at.
I had a quick question. You said that you're going to send us a bunch of practice problems, but you're
That's
not going
right.
to send us a practice exam like you've done in some other classes?
No, you'll just have practice problems. The exam will have 3 or 4 problems. We'll talk about it on Thursday.
All right.
Kinetics of. I also need to tell you the location of the exam, right? So that I'll figure everything out by Thursday. So today we get into kinetics of particles, and what we are looking at when we're talking about kinetics is what causes the motion. What causes the motion? It's always forces. So it's basically the study of the causes of motion. All right, everyone can hear me okay? See my screen fine, right? There might,
Yep.
Internet has been going on and off, so if that happens, just bear with me. All right. Study of the causes of motion, and then we have our famous equation that the sum of all forces on a body is going to equal the mass times the resulting acceleration of the body, right? And what law is this? It's Newton's second law. All right, so let's write it out in words because I'd like to be complete, right? So if the resultant force acting on a particle is not zero, right? So when is it zero? When we're looking at statics, when stuff is now moving, right? So here we have movement. The particle will have an acceleration proportional to the magnitude of this resultant force and in the direction of the resultant force. Right, and the way that we work with this is that you want to always express your forces in what's known as a Newtonian frame of reference. Whereby the reference itself, it might be moving, but it's not, accelerating or moving. But we can use the accelerations that we've defined as we looked at them in kinematics. Right, because there you completely describe the motion of the accelerations in those moving frames. All right, and usually this is valid for a constant mass system. Right. The next thing we want to define, but this we're setting this up to look at it in the next couple of lectures. We're not concerned with it today, and we're not concerned with it for your exam, is linear momentum. I think of this as a movie trailer for what's upcoming for the next movie that we're going to do. Right, so another way to write Newton's second law is basically, you have your forces, right? That's equal to the mass times acceleration, right? And then you can write your acceleration as what, right? You can write your acceleration as dv over dt, right? But then we know that this mass is constant, right? So you can put the mass inside and you get d of mv over dt like that. And this mv can be written as this new vector called L, where L is basically the linear momentum of the particle, which is basically just the mass times the velocity vector. Right? So if we looked at it, basically if your particle's traveling along some path, right, it's got a mass m, and its velocity is always tangent to the path, right? So you can have this linear momentum, which is in the same direction as your velocity, right? Talking about linear momentum, you get the concept of the conservation of linear momentum. Right? That states that if the resultant force on a particle is 0, the linear momentum of the particle remains constant. When you say it remains constant, because it's a vector quantity, we mean it remains constant in both magnitude and direction. All right. Just quickly looking at the units. This is just, we usually don't do this because you guys, where you are in your engineering education, this should be pretty obvious to you. So, when you're talking about these units, you have 4 primary dimensions. Right? You've got force, mass, length, and time. What you can do is you can choose any of these 3 arbitrarily, right? And then the 4th will comply with Newton's second law. Right, and we've seen this a lot. You have your SI units, whereby 1 Newton is equal to 1 kilogram times 1 meter per second squared, which is just 1 kilogram meter per second squared, like that, right? Okay. All good. All right, so next, let's get into equations of motion. Per second squared, right? Really need to be able to display the notes before moving on to the next page so that you guys can catch up. All right, next we go on to equations of motion. right? And all the equations of motion are basically just the equations that result from the use of Newton's second law, right? And make sure everything is in vectors. What that means is you can express everything as a vector form depending on the coordinate frames that you've chosen, or you want your equations typically in two perpendicular orthogonal directions, right? So what that means is that one can use scalar component equations. Right? For example, when we look at our favorite rectangular components, right? You can write everything in terms of I, J, K, right? So what does that mean? So that means that you can have all of your forces summed in the I hat plus all of your forces summed in the J hat plus all of your forces summed in the K hat direction, right? And this summation sign distributes throughout inside the bracket, right? You guys understand that this means that all the forces are summed in the X direction, all the forces are summed in the Y direction, and all the forces are summed in the Z direction, right? That's going to equal your mass times acceleration, right? So you have your acceleration in the X, acceleration in the Y, plus your acceleration in the Z direction in the K. All right, and then you can just equate your I hat terms, J hat terms, and K hat terms on the left-hand side and the right-hand side, right? So that's what we meant when you can look at the orthogonal direction. So you have sum of forces in the X is equal to MAX. Sum of forces in the Y is equal to MAY. And sum of forces in the Z is equal to MAZ, right? And we've described these accelerations in when we were looking at the kinematics, right? Wait, am I messing up kinematics and kinetics again? No, we're looking at kinetics. All right. F of x is equal to, what did we say the acceleration was? It's just the twice rate of change of your position, right? So it's x double dot Fy is equal to My double dot, and Fz is equal to Mz double dot, like that, right? So it's the rate of change of the rate of change of the positions. All right, next what we get into is that when you're setting up your problems using, when you're in kinetics and you're setting up your problem in statics, what was the first thing that you had to do when you're solving a problem?
Free body diagram.
Free body diagram. And you have to do the exact same thing when you're looking at a problem in dynamics, but now you have an additional diagram that you need to draw as well. And that's called a kinetic diagram. So you have to draw a free body diagram for all of the forces. That's for the left-hand side of the equation. And then you have to draw a free body diagram for all of your accelerations. And that's for the right-hand side of the equation. All right. In statics, you didn't have to do the right-hand side because the accelerations are zero, right? So you have free body diagrams and, very important, our new friends, kinetic diagrams. So let's write out the steps when we're doing it, right? So the steps that we have to follow are very similar to when you draw your free body diagram, right? You must isolate your body, right? You must draw out whatever coordinate system that you're using, right? You must have all of your applied external forces, right? Then you must have all of your reaction forces or your support forces, right? Always dimensions. Make sure that you stay consistent, right? And then the last step is this new thing that we have to do, which is the kinetic diagram. Right, so the first 5 over here, same thing we already know how to do, which is just the free body diagram, right? And the kinetic diagram is referred to as KD. All right, so if we take a look at a quick example, draw free body diagram and kinetic diagram for your block A, which we're just going to look at right now. So for block A, right? So you've got a block. Right, so sliding down. Right, let's say that this angle that it makes with this horizontal is 15 degrees, and then let's say that this angle with the horizontal is 25 degrees. Then you've got one pulley over here. And then you've got another pulley on the body itself. You've got another pulley up top, and then there's this body on top over here, which is sliding on that straight surface, right? So you've got the body B, and you've got this body A, right? And you've got a rope, which is that, right? Terrible drawing. The rope is taut, all right? Okay. Now, let's look at your body A and draw out the kinetic, the free body diagram, right? So when you're drawing the free body diagram out, right? So let's say if BD like that. Right, so you got there, got one pulley here, another pulley there, right? And let's draw our coordinate system such that the x-axis is along that sliding plane, right, over here. Okay, so now, what are all the forces that act on A? Right, let's go one by one. I'll let you guys drive and tell me.
Weight.
Weight, straight down. So let's say that that's MAG, like that. What else?
Normal.
Normal, which one? So you'll have 2 normal forces, right? You'll have a reaction for the block A itself and for the block B, right? So let's draw both of those. So you have normal force NA, right? And make sure you let everyone know that that's perpendicular to there. And then you'll have a normal force due to your body B as well, right? So MB like that, right? And then what else? What else would you have? So we're assuming nothing. So there's friction everywhere.
So the friction force along the bottom line.
Bottom line, right? So assuming that this guy moves down, the friction force is going to be opposite, right? So say that's the friction force. Let's call it FA like that, right? Because you'll have another frictional force, right? Due to this body B over here. And here it might be hard to know what direction the stuff acts in. So we can just assume for now that is going to be downwards, right? It might be upwards. If this is moving downwards on the body B itself, the friction force will be upwards, right? And then that frictional force will have equal and opposite onto here, right? So you'll have FB like that, right? So you have this is 25 degrees. You also have this angle, which is 15 degrees. All right, what else? Are we missing something?
Tension.
The rope.
All of the tension from the rope, right? So you'll have one tension component from this part here, right? You'll have, and tension always acts away from wherever you're at, right? So another tension force like that, another tension force like that. This one gets canceled out. So another tension force is like that. And then you'll have another tensile force like that, right? All good? This is just straight stuff off from statics that I'm sure that you guys have seen before, right?
Which one did you say cancels out?
These two, when you write it out, this tension force, these two will cancel out, right? But for all intents and purposes, forget I said that. They don't cancel out.
Okay, sorry.
Just always draw out all of your forces, all right? What I meant was that this tension and this tension will cancel each other out, right? You can consider the rope to be on there.
Yeah.
Anyway,
I follow.
yeah, all right, easy part. This is the easy part, which you know how to do, right? So what we have to do is just do the new part where we draw the kinetic diagram, right? So you draw the body again. Right? And all you have to do, guys, is super simple. Whatever frame you've chosen, be it rectilinear, rectangular, be it normal, tangential, or be it polar, just have to write out the accelerations in that way. Here, we're using rectangular coordinates, right? So all you have to do in whatever coordinate frame that you've chosen, you'll have an MAX and you'll have an MAY. That's it. It's that easy. Then you're set up to fully solve the problem. What's the first thing though? What can you say about one of these accelerations?
MAY is 0.
MAY is 0. It's not going to be moving on up and down in the y direction, right? So MAY is going to equal 0. That's something you do when you're doing your analysis, right? Okay. Any questions? All right, let's move on to another example. So now we have a rod which is rotating. And then on this rod, you have a collar that slides on it. Right? Say that the rod is A, and let's say that this collar is B, right? Let's say that this angle is theta, and the position relative to this point O of the collar B, of the center of the collar B, let's say that it is R, right? And the questions, what we want to do is that we want to draw the free body diagram and the kinetic diagram for collar B. Right? And what we're doing is we're assuming no friction between rod and collar. And this angle theta is basically increasing, right? So now the proof is in the pudding. You have r and theta, right? So we use polar coordinates, right? So draw out your free body diagram, specify your coordinate system. So your coordinate system is such that ER like that, and you have your E theta perpendicular to it, right? Then what are the forces that are acting on the collar B? I guess my notes is wrong. My notes show a frictional force. So there is no friction, right? Because you said that there's no friction over here. So you'll have weight mg. What else?
Your normal force.
Normal force. You will have a reaction with it moving upwards, right? And it'll be in the bottom side, right? So you'll have normal force. You know, from the setup of the problem, we know that this angle is theta, 90, right? That means that this is 90 minus theta, so that means that this angle is going to equal theta as well. All right, that's it. That's your free body diagram. And then you just write out your accelerations, which we did last week, but now you just put mass on them and you're done. So you'll have an MAR and then you'll have an MA theta, right? So this is going to be the crux of your exam next week. Be figuring out what coordinate system to use for your problem, and then, you know, doing your kinematics and then doing your kinetics for solving the problems. All right. So just to complete, yeah, go ahead, Mr. Ashford.
So this stuff is going to be on the exam?
That's right. Everything that we're doing today is going to be on your exam. So today and the homework that's going to be assigned today, your exam is going to be homeworks 2 and 3. All right. We're not taking an exam on statics. Homework 2 and homework 3 is going to be what's there in your first exam. And I will be assigning homework 3 today. Just got caught up with moving around this morning. All right, so let's just complete the picture, draw out our particle free body diagrams, and remember, recollect what the accelerations are so that we don't have to go back and look at our notes for kinematics, right? So let's first look at our normal and tangential components. Right? So typically you'll have, you know, usually when you're looking at normal and tangential components, you'll have an arced path, right? That's another hint for you to know. So have something like that, right? Then you've got your tangential direction. So let's say that that's a mass m, right? So you have your tangential direction, and then you'll have your normal direction. And remember, when you're using tangential and normal components, radius of curvature comes in. So the normal component is always pointing inside your curve, all right? And that's your normal direction right there, right? And you can do, you'll have to figure out your sum of forces in the tangential direction, and then sum of forces in your normal direction, right? And that's your free body diagram. And then for your kinetic diagram, right? Your M, it's the same thing. You'll have a tangential component, and you'll have a normal component with a straight line, not like that weird curvy line that I just drew. That, right? So you have all your accelerations in the tangential and your acceleration in the normal direction, right? And to complete our story, we always call our particles with P, right? So sum of forces in the tangential direction is equal to mass times acceleration in the tangential direction. Similarly, sum of forces in the normal direction is equal to mass times acceleration in normal direction. But we know these things. We looked at it last week. Acceleration in the tangential direction is just the rate of change of velocity, right? So dv over dt. And then your acceleration in the normal direction, that guy, right? mv squared over rho, whereby that's your radius of curvature. Right? And if you guys, if this looks weird to you, just go back to your notes from last week. We derived everything last week. All right, and then let's look at the kinetics when you're looking at your radial and transverse, so your polar coordinates, right? So here, well, I guess I'll do this on a new page. Ooh. Are you guys done with this one? Right, move on.
Yes.
All right, so now again, you've got your curved path, but now you always need to do radial and transverse with reference to an origin, right? So origin like that. And then you draw your position vector to wherever your particle is, right? So let's say your particle P with a mass M. And then in the same direction as this vector R, right? You have all the forces which act in that direction, and then you have the perpendicular direction to that. Typically, this is in the perpendicular one is in the direction in which your angle is increasing usually. F theta, like that, right? So these are all of your forces. Then you have a kinetic diagram, right? So you've got 0.0 again. Whoa, wrong color. There, right? So everything's the same. Theta, R, but now you're looking at your accelerations, right? So you have your MP, MAR, and MA theta, like that, right? So we write the expressions out. FR is equal times M times AR. And we know we derived this AR was equal to R double dot minus r theta dot squared, and f theta is equal to ma theta, which was m times r theta double dot plus 2r dot theta dot. Good. All right, let's get into some problems.
I'm sorry, could you repeat what P exactly means?
Just the particle, just the point P,
Okay.
particle P, yeah. P just refers to the fact that we're looking at particles right now. What that means is we might be given whole bodies, but we only need to look at one point on that body. The whole body can be broken down into a particle. When we start looking at rigid body motion, which is going to be, right now it seems like the distant future, but time comes pretty quickly. That's what we do in the second half of the course. And that's my favorite part of dynamics. That's where the fun really starts. But anyways, all right, you guys get me excited really easily.